So we're going to learn about enthalpy of reactions, and that's this right here, right there. And you will learn that enthalpy is just a fancy word for heat. Chemists use the symbol H to represent enthalpy, and you'll see this little delta H here very often. This symbol is a Greek D, capital D. It means delta, which also means change in, and it can also mean final minus initial. So delta H for a reaction, Rx then stands for reaction, would mean we're going to add together the heats of formation of the products. That's the final is the products. And then heat of formation of the reactants. Reactants are what we start with, so that's our initial. So it's final minus initial. I will explain what all these things mean. This symbol here is a Greek S. It stands for sigma. Oops, not signima or sigma. It's a Greek capital S. It's sigma, and it means the sum of. The little superscript right here, this tiny superscript right there, put that in quotes there, just means standard conditions. And standard conditions, you don't have to memorize this. It's 25 Celsius and 1 atmosphere. This is a pressure unit that we will learn about more next chapter. I'm just giving you some background information right now. Okay, and the way that we would read this whole equation right here is right here. The standard heat of reaction, that's this piece right here, is equal to the sum of the heats of formation of the products. This is the sum of the heats of formation of the products minus the sum of the heat of formation of the reactants. This right here is the sum of the heat of formation of the reactants. And again, don't worry, this is all new. It's like a foreign language, but we're going to go over it. You're going to learn everything. Okay, chemists define this delta HF naught. Oh, by the way, this little zero up at the top, we call that naught. So delta HF naught, which is the heat of formation of any substance in its standard state at standard conditions. Chemists define the heat of formation of all pure elements in their standard states as being equal to 0. Enthalpy is a relative scale. We'll talk more about this. It's a little confusing at first. It's a relative scale relative to our definition that all pure elements in their standard states are considered to have a heat of formation of 0. And then we measure the heats of formation of all other substances relative to the pure elements. We do a bunch of reactions, we measure the heat produced, and then scientists publish heats of formation for non-pure elements. Okay, so here's an example. We want to find the heat of formation for water. We measure this by reacting pure hydrogen and pure oxygen and finding the amount of heat produced per mole of water produced. If we're going to react hydrogen and oxygen to make water, the reaction looks like this. Hydrogen gas, oxygen gas makes liquid water. That little L just stands for liquid. The heat of reaction, remember, is products minus reactants. So the heat of reaction for any reaction, no matter what kind of reaction it is always products minus reactants, where we use the heats of formation in this equation. So let's look. I'm going to now turn these symbols into a new set of symbols. So we're going to do the products. The product is water, so I have the heat of formation of water minus the heat of formation of the reactants, H2 and O2, and I have to include the coefficients. So notice the coefficients here match the coefficients right here. If I look at this, this is equal to the heat of formation minus, remember, pure elements are defined as having a heat of formation of 0. So this right side is all equal to 0. So when I do the subtraction, I just get back the heat of formation of water in its standard state. So the heat of reaction for this reaction is also equal to the heat of formation of water, because the definition of heat of formation is forming a compound from its elements in their standard states. So I would run that experiment, measure the heat, and then I would publish the heat that I found per mole of water. I would publish that value in a book. Okay. So these are calculated for compounds and then put into books for scientists to use for other calculations. You can also look these up online. So here's an example where we have a bunch of substances, and this should say delta HF0. They just didn't put it in correct format here. So this would be the heat of formation in kilojoules per mole for all these different compounds. Okay, and you don't need to copy any of those down. I'm just showing you, you can look these up online. You can look these values up in books. These values are public information. You can find them. Okay, for our purposes, when we are figuring out how to write a heat of formation reaction, we're going to assume all elements are written as single atom formula units, except for sulfur, which is S8, and then Hofbrinkel. Hofbrinkel. These are all diatomic elements. You will probably have to memorize that part. But Hofbrinkel, anytime you hear me say Hofbrinkel, I'm talking about the diatomic elements. Note, when these are ions, they are not diatomic. This is just when these elements are by themselves in their pure form as molecules. No charge, they are diatomic. Okay. Now, another thing you should know is that all elements are solid at standard conditions, except the noble gases, and I'll show this to you in class because it's a pretty easy pattern. The noble gases, most of Hofbrinkel, just bromine and iodine are not gases. So of all of the Hofbrinkels, they're all gases except for bromine and iodine. And then the only other gases are the noble gases. And then we have two elements that are liquids, just bromine and mercury. So iodine is a solid because we said all elements are solid except for these and these. So there are only about, I don't want to give a number, but there are less than 20 elements that are not solids. Okay, so here's a problem. You want to write the reaction for forming each of the following from the elements that produce the substance. So we have methane, and you look and you say, oh, I've got carbon and I've got hydrogen. How do I write that reaction? Well, carbon, we know, is not one of these things. So carbon is going to be solid. It's not Hofbrinkel or sulfur, so it'll have a single atom. So I will have solid carbon. And then hydrogen. The other element that forms this is hydrogen, and we know hydrogen is part of Hofbrinkel, and hydrogen is a gas. We have to pay attention to who are the gases, who are not. So I have chlorine and hydrogen making CH4, and now this is not yet balanced, so we have to balance the reaction and put a little 2 right there to make that balanced. And the heat of reaction for this reaction is also the same thing as the heat of formation of methane, because I'm forming methane from its elements, and that's defined as the heat of formation of a compound. And then these values are put into tables that are published. They're done by scientists, and we can get them on the web, we can get them in chemistry books. Okay, next one. Forming ethanol from its elements. So I want you to write the reaction for forming ethanol from its elements. So first identify the elements. We've got carbon, hydrogen, oxygen. Carbon is not sulfur or Hofbrinkel. So carbon is single element, single atom element. It is a solid because it is not one of these. It's not a noble gas, it's not one of these, it's not bromine or mercury, so therefore carbon is a solid. Hydrogen, so I'm going to need all the elements that are in here are my reactants, so I need hydrogen as well. Hydrogen is part of Hofbrinkel, so it'll be H2. Hydrogen is a gas, so I will write that as, the 3, you'll find out why that's there in a moment. It's because I already balanced this for you. 3H2, and then some oxygen. So let's see, half of an oxygen. Ooh, all of a sudden there are halves there. Now it's O2 because oxygen is part of Hofbrinkel. We put the G there because oxygen is a gas, and that will form our C2H5OH. You would not know that ethanol is a liquid. I would tell you what compounds are. I will tell you the solid, liquid, gas, or aqueous for all the compounds. But for pure elements, you should be able to figure out whether we have a solid, liquid, or gas, and whether they are monatomic, listed as single atom elements, or whether they're diatomic or sulfur, where we have the S8. Now notice I did not balance this out so that I would have whole numbers here. That's because for the heat of formation, I need to have only 1 mole of product. I can only have 1 mole of product. So to have 1 mole of product, I have to have only a half a mole of oxygen. And the heat of reaction for that reaction is the same as the heat of formation of ethanol. If I had a 2 here, if I did, but I don't, if I had a 2 there, the heat of reaction for this reaction would be twice the heat of formation of ethanol. Okay, another kind of reaction that we'll talk about is heat of combustion. And I've given you this whole definition here. You don't have to write any of it out. Combustion is just burning a substance in oxygen. We combine each of the elements. So for this substance, if I were burning this with oxygen, I would form carbon with oxygen, hydrogen with oxygen. Oxygen's already there, so I'm not going to form oxygen with oxygen. We'll just have oxygen as a reactant. So we have whatever chemical we start with, we add oxygen to it, and then we form whatever elements were in the original substance, we add oxygen to each of those to form a compound. So let's try one. Write the reaction for the combustion of methane, CH4, and then we're going to look up the values for the heats of formation for all of the substances in there to calculate the heat of combustion for methane. So first we just want to do the combustion reaction. Combustion says you take your substance, there it is, CH4. Now, did I tell you it was a I did not tell you that methane was a gas, so I just added that in here. So combustion of methane gas. Actually, I think we had that up here. Yep, we did. I had given that methane was a gas up here. So methane, we're combusting methane. Combustion means you add oxygen. And remember, oxygen is part of Hofbrinkel. And you'll find out in a moment why there's a 2 in front of that. So I have oxygen, which is part of Hofbrinkel, so I need O2. Oxygen is a gas because it's one of those elements that I told you is a gas. Gases include Hofbrinkel minus these and noble gases. Those are our only gases. So for combustion, we add oxygen to the substance, and then we form products that are oxygen combined with each of the elements separately. So for this one, I would form C with oxygen. Can you think of a substance you know of, a common substance that has carbon and oxygen? If you haven't figured it out, it's carbon dioxide. And can you think of a really common substance that makes up over 70% of your body mass, where hydrogen combines with oxygen? That would be water. Okay, and then I had to balance the reaction, so I have these 2's here. Okay. Okay, so we get our reaction, and I asked you for a heat of combustion right here, heat of combustion. So you'll have to know combustion means you add oxygen, and then you form products. We're almost going to always form CO2 and H2O. So if you just memorize CO2 and H2O, you'll be fine for this class. We won't do other combustion products. Okay, we don't need to look up the value for oxygen, but we need to look up all these values. Why don't we need the value for oxygen? Do you remember? Because all pure elements in their standard states are defined to have a heat of formation of 0. So we know automatically oxygen is 0. Now you could look in the Tro book, Appendix 2. You don't have to. You could also look online for the heat of formation for the other substances. I'm just going to show you what this would look like. Okay, so when you look in a book, you would see tables like this with a whole bunch of compounds ordered by substance, by element, and then you'd have the heat of formation right here. Later you'll learn about Gibbs free energy of formation and entropy. For now we don't have to worry about those, but you basically look these data up in tables. Or again, online you can find. Okay, so I looked these data up for you. You can fill those in. And now, remember, we have heat of reaction, which is the same as heat of combustion for this reaction. So when you see heat of reaction, that's a generic heat of reaction. This one is a more specific type of reaction. This is the heat of combustion for methane, which is the heat of reaction for this reaction, because this reaction is the combustion of methane. So remember, heat of reaction is products minus reactants. So I'm going to use my reaction, and this means, oops, that always happens. I need the heat of formation of the products. And where did my reaction go? Here we go. Here are my products. So I need 1 CO2 and 2 waters. And I subtract the reactants. The reactants are right here. And I always multiply a chemical by its coefficient. I multiply the heat of formation by the coefficient for the chemical. All right, so that's our generic formula for this. And then we plug those numbers in. This is plugging the numbers in. Now notice I did 1 mole times the heat of formation of CO2 because there's really a 1 in front of here. So it's the 1 mole times the number of kilojoules per mole for the CO2, 2 moles because I had 2 waters, times the heat of formation for water, and then I subtract the heat of formation of the reactants times their coefficients. Biggest mistake students make is to forget to put the parentheses around here, and then they add something and they don't know how to distribute the negative sign through here. So we'll do some practice in class where you get to do that. Okay, next problem. Write the reaction for the combustion of ethanol. And we learned above that ethanol is a liquid. So we're going to have ethanol, liquid. We're going to add oxygen because that's a definition of combustion reactions. I have hidden the balancing part here, so you'll get that practice. And remember, we always form CO2 and H2O. Oh, and the H2O we form for this class would be liquid water. Then you balance this. If you want to take a moment to balance that, you can. There's the balancing. You can look in the TRO appendix, or as you know, I'm going to put this in here, so you could just copy these numbers down. I would look these up in an appendix, or I would look these up online. You could just look up heat of formation of ethanol, and this number will pop up. It sometimes is a little bit off, but basically this is the number you would have. Okay. So now the heat of reaction is the products. These are your products minus your reactants. Here's your reactants. And then you just plug these numbers in and do the calculation. So I just plug those numbers in to this equation right up here, and I get this value. Oh, and notice I'm keeping this to the tenths placeholder. I don't count sig figs. This is all addition and subtraction. So I have to keep everything to the tenths place. In this last one, let's look at sig figs. Oh, again, tenths placeholder. Notice the answer has 4 sig figs, and here I've got 4, 4, and 3 sig figs. I don't count sig figs when I'm adding and subtracting. I only count sig figs when I'm multiplying and dividing. Okay. I accidentally deleted the S right there. Okay, new topic, Hess's Law. This is when you add 2 or more reactions together. We know that the heat of reaction for those 2 added reactions would be the sum of the heats of the reactions of the summed reactions. I'll explain that in words. You'll see how this works very shortly. So if I say I want you to find the heat of reaction for this reaction, and I've given you the heats of all of these reactions. This looks really hard at first, but it's actually fun. It's like you're combining reactions and figuring out what you need. When we look at our original reaction, we look for a chemical that appears in only one of these 3. So methane, we'll notice, only appears here. If you look at hydrogen, hydrogen is appearing here, oops, and here, and here. So we're going to ignore the hydrogen. We're going to look at the methane. And for methane, it says we are trying to get 2 methane because our original reaction has 2 methane. So then I look at these and I say, oh, reaction 2. It's got 2 methanes on the wrong side. So I'm going to multiply this reaction by 2 and then reverse the reaction So I'm going to make the reaction go in the opposite direction, which means I'm going to put a negative sign. So I need -2 of reaction 2 because I have to reverse to get the methane on the reactants instead of the products. And I need 2 methanes. This has only 1. All right, let's look at ammonia. So ammonia, I need 2 ammonias on the left side. I have 2 ammonias on the right side. What do you think I'm going to do? I have 2. I need 2, but they're on the wrong side, so I multiply that by -1. Cyanic acid. All right. 2HCN on the right side, 2HCN on the right side. The chemical's the right number. It's on the correct side, so I just need 1 of those. I'm going to need 1 of reaction 3. Now here you'll notice what I had right here is exactly what I wrote here. -2 of reaction 2, -1 of reaction 1, and 1 of reaction 3. Now I color-coded all of these. I'll explain that in a moment. But Hess's law says whatever I do to a reaction, I would do that to the delta H, and then I can add the delta H's. If I multiply a reaction by -2, it's like I've doubled the reaction and reversed it. So I'm going to double this and change the sign because I reversed the reaction, so I have to change the sign. I've doubled the reaction, so I'll have to double that. So I will have -2. Oops, it's this one actually because it was reaction 2. So I have -2 of -2 times -74.9. Reaction 1, I reversed reaction 1. If I reverse a reaction, you change the sign of delta H right there. So I have -1 of this heat of reaction. And then I had 1 of reaction 3. So I just need that 270 right there. Now, all I have to do is add these up, and that will give me my heat of reaction for this reaction right here, which is the reaction I was trying to find. When I add those all up, I get 511.9. And now let's look at what happens here. You have to do this step where you actually, whatever you did to each reaction, you write it out. And then you have to add all these reactions up. I color-coded this so that hopefully you can see that I have 2 CH4s, and those carry down. I have 2 HCNs, and those carry down. Now, right here I have 7 H2s. And on the left side, I have 1 H2. This is just like a mathematical equation. 7 minus the 1 leaves me with 6 H2s. Now the nitrogens, notice I have 1 here and 1 here. They cancel each other out. The carbon here and here, those cancel each other out too. And I literally get back the reaction that I was looking for right up here. Those are exact matches. Okay, last problem. Let's just look quickly. So we've got zinc oxide right here, only appears once. I need 2. I have 1 on the wrong side, so what am I going to do? I'm going to multiply that reaction by -2. Carbon dioxide, CO2. I need 2 on the left side. I have 1 on the left side, so what do? I'm going to multiply that reaction 1 by 2. The zinc carbonate right here, I need 2 on the right. I have 1 on the left, so what do I need to do? I need -2 of reaction 3, so I'm going to multiply reaction 3 by -2. Now, I have again color-coded all of the chemicals in here. If you want to get a colored pen, you can use a colored pen. You don't have to, but I will show you over here what we did. And then over here. Okay, so -2 of reaction 2. I wrote those all down in different colors so that you could identify what's going on and what's canceling out. So reaction 2 was 43, but I multiplied that by -2 because that's what I did to the reaction. And then reaction 1, I needed 2 of reaction 1, so I multiply the heat of formation of reaction 1 by 2. And then I need -2 of reaction 3, so I need -2 times -70. And I sum these all up to get positive 20 kilojoules. And I was looking for the heat of reaction for this reaction. When I sum all of these up, I actually get that. And right here, I see the heat of reaction for this reaction will be 20 kilojoules. Let's look at how things canceled out here. All right, my two zincs gave me two zinc oxides give me 2 zinc oxides. There's my carbon dioxide, 2 and 2, and there's my zinc carbonate, 2 and 2. So what happened to everything else? Let's look. I have 2 zinc hydroxides here, and I had 2 on the left, so they canceled. I have 2 carbonic acids here, and I had 2 on the right. They canceled. I have 4 waters here, but I have 2 waters and another 2 waters. They cancel, so the waters cancel out. And there you have it.